Okay, welcome to lecture 31. In this lecture, we're going to talk about device isentropic efficiencies. Specifically, we'll talk about isentropic efficiencies for a compressor, a turbine, and a nozzle. The picture I have on the screen here is of a typical jet engine. The components you can see here, you've got actually right up at front here is a nozzle. So the flow comes in through here. Actually, it'd be coming in through here. You go through a set of compressor blades. These are to compress the flow. It'll compress the flow, raising the pressure and temperature. There's some work that's done to make that happen. So you're putting some energy into the flow. Then you go into a combustion chamber. Here you're adding fuel and igniting it with the air. This raises the energy within the air, right? So we have a lot of energy now in the air here at this point, and then we pass it through a set of turbine blades. The turbine blades extract enough energy to rotate the shaft, right? So if it's a jet engine, you just want to have enough energy so that out of the shaft, this is all mounted to the same shaft. You just want to have enough energy in the shaft so that you can run your electronics and hydraulics, etc. Right? If this was like for example, a steam turbine, what you'd want to do is have enough energy, or if this was to power some sort of piece of machinery, what you'd want to do is have a lot of energy coming out of here to rotate that shaft, so you get a lot of shaft power. For an aircraft engine, you would just pull out enough energy from the turbine to keep, like I said, the hydraulics, the electronics and such running, but most of that energy you'd want to keep in the flow and then have it leave the back end at a very high speed, a lot of kinetic energy so that you can provide a lot of thrust for the aircraft. Typically, the compressor compresses the material in many different stages. You can sort of see that here, a bunch of different stages in the compressor. The reason it's done little bit by little bit is because it's just more efficient that way. We'll talk a little bit more about that later. Same sort of thing with the turbine stage. You generally want to extract the energy from each set of turbine blades a little bit by little bit. You'll get more efficiency that way. If you go into Google and you type in Purdue AAE propulsion website, it'll take you to a nice sort of introductory website on propulsion, and I encourage you to take a look at it. It's kind of interesting. If you have some interest in this kind of field, definitely take a look at it. You'll learn a little bit more about aircraft engines and some of the components and such. All right, well, let's get into the material for today then. Again, we're going to talk about device isentropic efficiencies. We're going to start with a turbine. And the reason we want to talk about isentropic efficiencies is because it gives us a point of reference for determining how well our actual components are operating. So let's say we have a turbine like you see on the picture here. So we have a turbine. The reason we're doing these efficiencies is because we may have our actual turbine, so it operates from state 1 to state 2. We get a certain amount of power out of it, but we'd like to know, just how well is our turbine operating. So to provide a point of comparison, what we want to do is compare it to a turbine that's operating isentropically. Why isentropically? Well, as you already know, often we assume that turbines are operating adiabatically, right? So we often assume adiabatic operation. And then the other thing that we'll assume is that under the best case scenario, the turbine is also operating in an internally reversible manner, right? If it's internally reversible, there are no inefficiencies for the turbine while it's operating. So it's like the ideal condition, the frictionless condition. There's no inefficiency. So if it's adiabatic and internally reversible, that means it'll be isentropic. So that's why we're calling these isentropic efficiencies. It's because that will be the ideal case that we're going to compare against. And so from this, we then define in this case, the turbine's isentropic efficiency. So that's this eta term here. It's the actual power that we get out of the turbine. So our real life turbine, how much power do we get out? Divided by the power that we would get out of that same turbine if it was operating isentropically, again, adiabatically and reversibly. This ratio should always be less than 1, right? Because the isentropic case is the ideal case. That's where you're going to get the most power. The actual case will give us less power. In real life, typical values for turbines, it depends on their design and such, but it can range between about 70% and even into the 90 percentages. So maybe on the order of 95% for a very well designed turbine. So you can get actually quite efficient operation from turbines. So how do we determine these powers? Well, the way we do that is we apply the first law to the control volume shown in the picture there. So let's do that. And in the first case, what we'll do is we'll go from state 1 to state 2. Okay, this is the real life operation. State 1 to state 2 is the real life operation. So let's write out the first law in its full form, as we've done many times before. I'll only write out the first law in its full form this first time through. The other cases that we'll take a look at, I won't start at the very beginning just to save us a little time. Okay, so here's our first law equation. The time rate of change of total energy in the system is going to be 0 because we're going to assume steady state operation. I'm not interested in transients here. I just want what's the operation for the turbine in steady state. We'll also neglect kinetic and potential energy changes. That is, again, pretty typical. Those terms are often very small compared to the specific enthalpy term. We're assuming adiabatic operation. So that means that there's no heat transfer. And then we can rearrange that equation. Oh, and the other thing I should say is that there's only one inlet and one outlet. And from conservation of mass, you can show that m dot 1 is equal to m dot 2, and I'll just call it m dot for convenience. Okay, so then the power that we get out of the turbine will be m dot times h1 minus h2. So this is the actual case. Okay. We can do the same analysis, and by the way, you've done this sort of thing many times, so this shouldn't be a surprise. So we can do the same analysis for the isentropic case, but in this case, we'll go from state 1 to state 2s. The s just indicates that the process is isentropic. Okay, so if you do the same first law analysis, it'll look exactly the same, except instead of 0.2, it'll be 2s. So this is the power out. For the isentropic case, it'll still be m dot h1 minus h2s. Well, we can take both of those expressions, plug them back into our expression for the isentropic turbine efficiency, and then what we'll get is the following. Actual is h1 minus h2 over isentropic h1 minus h2s. Okay, so that's how we would find the isentropic turbine efficiency. You don't have to memorize, h1 minus h2 over h1 minus h2s. If you just remember that it's the actual power divided by the isentropic power, if you can remember that, and I don't think that's too hard to remember, and then just knowing from the first law, you can write out what the powers are in terms of enthalpies, then you can always get back the turbine efficiency. It's a couple of extra steps, but you don't have to memorize quite as much. Now, to find the H1 and H2 and H2S, typically you generally know what the inlet conditions are. So H1 is often known. You usually know the incoming pressure, the incoming temperature, so you could calculate or use property tables to find H1. For H2, often we get a measurement of what the outlet conditions are. So we might know the pressure and temperature at the outlet. So H2, again, we could look up from property tables. H2S, that one's a little trickier. There, what we'd have to do is, again, assume that the process is isentropic from 1 to 2, or 1 to 2s, I should say. Let me write some of these things down. State 1, usually P1, T1 are given. Typically, state 2, typically P2 and T2 are given. When I say given, they're usually measured. So you actually make a measurement of those things. So for those things, you can look up H1 and H2. These come from property tables. Okay. To get to state 2s, What we typically know there is we generally have the same outlet pressure as state 2. P2S is generally the same as P2. That's because the turbine boundary conditions are often just the same. You're still operating between the same pressures. So that's generally known. And then since we know that we're operating isentropically, we know S2S is equal to S1. This is the isentropic assumption. So now we have two properties. From there, we can again use the property tables to find H2S. It's just that instead of temperature, we're given specific entropy. From those property tables, you could also find T2S while you're at it. So you can find both of those and any other properties that you're interested in. So that's generally how one would find the isentropic turbine efficiency. Let me just go ahead and sketch what this might look like on a TS diagram. We're going to go back up here. What I've drawn here are some isobars. So generally across a turbine, the pressure drops. So this will be P1 up here. That's an isobar for state 1. And then here we have P2. P2 is less than P1 for a turbine. And let's say that our state 1 is right here. This is our T1. And then our corresponding specific entropy is down here, S1. I should move that over. And then for a real life scenario, what happens is we drop down to pressure 2. Well, the entropy will increase. If you go back to the entropy equation, let me go ahead and write this down over here. Entropy equation, just so you can see it. Okay, so there's our entropy equation. Time rate of change of entropy inside our control volume will be 0 because it's steady state. The incoming and outgoing entropies will be m dot times S1 minus S2. The heat transfer term is going to be 0 because it's adiabatic. Let's see if I can spell adiabatic. There we go. And so when we solve for the entropy production term, we'll get sigma dot is equal to m dot S2 minus S1. Right? Or let me write it a different way. S2 is equal to S1 plus sigma dot over m dot. That's just another way to write that. So you can see that if you have some irreversibility, so if sigma dot is greater than 0, if it has some irreversibilities, then S2 should be greater than S1. So when I go back up to my TS diagram, state 2, it'll have a specific entropy somewhat larger than S1. So this could be our state 2, for example, in our drawing. So our process, our actual process would look like that. And here is our T2. Now for the isentropic process, well, we know that if it's isentropic, S2S should equal S1. Another way you can see that is down here from the entropy equation. If we're dealing with the reversible case, sigma dot will be 0 and S2S would be equal to S1. So for that case, our state 2S would be right here. That's 2S because S1 is equal to S2S. We're just dropping vertically because it's isentropic. The entropy remains constant down to the same isobar for pressure 2. And then here is our temperature, T2S. So you can see that the temperature for the isentropic case should actually be less than the temperature for the actual case. And the reason for that is because what happens when it's isentropic is it's just there's more energy. There's a more efficient transfer of energy from the flow energy that's kind of related to the pressure and temperature, the internal energy within the fluid passing through the turbine. There's a more efficient transfer of that energy into shaft energy. And so there's less energy to go into the internal energy. And so that's why the internal energy is smaller when you have a higher isentropic efficiency. You're just extracting more shaft energy out of the flow, and so there's less energy to go into internal energy, and so the temperature is a little bit lower. Okay, hopefully all that makes sense to you. Let's move on then. Okay, here we're talking about the isentropic efficiency for a compressor or pump. We're going to analyze it in much the same way that we did for the turbine. So here we have our compressor. We have some inlet flow. Generally, that's the conditions there are known. We're going to put some power into our compressor in order to do work on the fluid. And then we have some actual outlet condition, that's state 2, or an isentropic outlet condition. And again, we're interested in the isentropic case because generally compressors operate in an adiabatic fashion, no heat transfer. And then for the ideal case, we want it to be internally reversible. And those two combined together make it isentropic. So that is our ideal case, is the isentropic case, for all the same reasons we talked about previously. So the way we'll define the compressor isentropic efficiency, and I put compressor or pump here because you can use the same idea for a pump. That is going to be defined as the power you have to put in if it's isentropic divided by the actual power you have to put in. Now it's upside down from what you have for the turbine. And the reason for that is because in the isentropic case, the ideal case, you have to put in less power than the actual case. Remember, the power is coming in here. So if it's ideal, you don't have to put quite as much power in than you would have to if it was the real case. Again, this ratio will be less than 1. Typical values for compressor efficiencies are lower than those for turbines. They're about 75 to 85%. So they're generally a little bit lower than what you might have for a turbine. Now the reason for that has to do with the fluid mechanics of the flow through the compressor or the turbine. From the inlet to the outlet, the pressure's increasing, right? Let me make a note of that. So P2 is greater than P1, right? When you're pushing the fluid into that higher pressure, it's more likely you're going to get larger viscous effects. This is what we call an adverse pressure gradient. An adverse pressure gradient is when the pressure that you're moving into is higher than the pressure that you're starting off with. You can get a lot of inefficiencies when you're pushing fluid into an adverse pressure gradient. For a turbine, P2 is less than P1, right? So for a turbine, that's called a favorable pressure gradient. When you're pushing fluid into a lower pressure, that's actually pretty easy to do, and there's less inefficiency for that. So in that favorable pressure gradient, like in a turbine, you would have less irreversibility. Those viscous effects aren't as significant. So that's why you get higher isentropic efficiencies for turbines typically than you do for compressors. It has to do with pushing fluid into a higher pressure region for a compressor and then those viscous effects. You'll learn more about that sort of thing in fluid mechanics. It's not something you really need to know about here for thermo, but I thought I'd just give you a little preview just so you're familiar with it. You kind of understand the physics a little bit better. Okay, so to find the powers associated with the actual and isentropic case for a compressor, again, you can apply the first law to the compressor, just like what we did for a turbine. I'm not going to go through those steps. I'm just going to give you the final result. So the power in actual will be m dot times H2 minus H1. And then the the power in, for the isentropic case will be m dot H2s minus H1. And then if you want to find the compressor isentropic efficiency, you just take the ratio of the isentropic, which will be the smaller of the two powers. You have to put less power in the actual case, and then divide through by the actual power that you have to put in. And again, just like with the turbine isentropic efficiency, you don't necessarily have to memorize this formula, as long as you can remember that for a compressor, the power you have to put in for the isentropic case will be less than the actual power. And then you know how to apply the first law, you could quickly come back up with that expression. And to find those values for H1 and H2 and H2s, again, these come from property tables. For example, state 1, you would generally know P1, T1, so you can find H1. State 2, again, typically you know P2 and T2, those would be measured, so you could find H2. And then for state 2s, the compressor operates between the same pressures as state 1, state 2. So P2S is equal to P2. Just like a turbine, the compressor operates between the same pressures. But for state 2S, that's isentropic, so S2S is equal to S1. And there again, you can find from property tables or the ideal gas model, for example, you can find what H2S will be. And if you're interested, you can also find the temperature for that isentropic case. That'd be T2S. So let me go ahead and plot these things on the TS diagram, just like what we did for a turbine. So here is our isobars. So for a compressor, we're increasing the pressure. So I'm going to put P1 down here. P2 is up here. P2 is going to be greater than P1. Recall that for the turbine, P2 was less than P1, but here it's greater because we're increasing the pressure of the fluid. So we'll put state 1 right there. There's our temperature T1 and our specific entropy S1. And then the entropy will increase as we go to state 2. That just comes from the entropy equation, just like what we had for the turbine case. So the entropy will increase, so that means we're going to move over a little bit. So state 2 will go to a higher pressure, and then we'll have a higher specific entropy. So that's our state 2. So our process looks something like that for the real case. And then for the isentropic case, the entropy, of course, remains constant. So S1 and S2S are the same. Here's our point 2S. That's vertical. And then if we put our temperatures, you'll see here, there's T2, and here's T2S. And just like what I talked about before with the turbine, the temperature for the isentropic case here is a little bit less than what it is for the actual case. What's happening here is when we put in the shaft power for the actual case, some of that energy is going into going into heating the fluid and not increasing the pressure. For the isentropic case, we're a little more efficient with it. We don't have as much energy dissipated into increasing the temperature, the internal energy. It's just more efficient, so we don't have to the temperature doesn't go up as much because we're not putting energy into heating the fluid. We're actually just getting it into increasing the pressure more efficiently. That is the case for the isentropic efficiency for a compressor or pump. Actually, let me just mention one other thing here. If we're dealing with an ideal gas, and this is true for a turbine as well, recall that for an ideal gas, the specific enthalpy is a function of temperature, right? So to find these specific enthalpies over on the right-hand side, if you're dealing with an ideal gas, what you would do is, given the temperatures, you can look up, here's the temperature here, here's the temperature there. You can go to the ideal gas tables to find the specific enthalpies, right? So you can use the ideal gas tables to find those. If you're dealing with a perfect gas, where the specific heats remain constant, then you can write a delta H as Cp delta T, right, for a perfect gas. So for example, H2 minus H1 would be Cp T2 minus T1, and for the constant entropy case, it's Cp T2s minus T1. Another thing that you could do is for the isentropic case, we know that ideal gas plus isentropic. For that particular case, if you go back to the notes, what you'll find is that we have this expression using the relative pressures where P2 over P1 is equal to the relative pressure at 2S, T2S over PR T1. Remember, this is specifically for an ideal gas undergoing an isentropic process. That's why I'm using the S here. If you go back in the notes, you'll see this expression for the relative pressures. In these kinds of problems, generally you know the pressures, the pressure ratio across the compressor. So you would know this side. You would generally know the inlet temperature. So you could look this up from the ideal gas tables. And then you could solve for this relative pressure at that temperature, and then go back to the ideal gas tables to see what temperature that corresponds to. So that's one way you could find the temperature and then the specific enthalpy for the isentropic case. Let's go on to the last topic. Okay, here we're talking about our last topic. It's the isentropic efficiency for a nozzle. So I've drawn a picture of the nozzle here. We have some inlet flow, and then we have our outlet flow. This will be the actual. This is the isentropic case. Just like with the turbine and compressor, we're going to assume that the flow through this nozzle is adiabatic. And for at least for the isentropic case, we'll also assume that it's internally reversible, and that gives rise to isentropic. So that's the point of comparison here. We're going to compare our actual nozzle performance to our isentropic nozzle performance. So the definition for the nozzle isentropic efficiency, what we're doing here, since there's no power involved like you would have for a compressor or a turbine, here what we're doing is we're comparing the kinetic energies of the outlet flow. So the purpose of a nozzle, one of the main purposes is to accelerate the flow. We want high velocities here typically in a nozzle. So what we're going to do is we're going to compare the actual velocity in the nozzle, or here it's actually the specific kinetic energy, to the velocity or specific kinetic energy you would have if the flow were isentropic. So that's how we're defining our isentropic nozzle efficiency. So actual kinetic energy at the outlet compared to the isentropic kinetic energy at the outlet. And you would expect that under ideal conditions you would have more kinetic energy going out here. Okay, and the reason for that is, again, think about as you go from state 1 to state 2 or state 2s, you're converting energy into different forms. So at the exit here, you'll have some energy associated with the kinetic energy of the fluid and then some internal energy of the fluid. And what you want to do is you want to make sure that most of that energy is going into the kinetic energy, not into the thermal or internal energy. So in the isentropic case, you'd get that conversion with higher efficiency than you would get for the actual case. And typical isentropic efficiencies for a nozzle are about 95% or even higher. It's a very efficient process. And again, the thing that causes the inefficiencies are these internal viscous effects within the fluid. So as the fluid is going from state 1 to state 2, there's some viscosity, and that dissipates some useful energy. It goes into being internal energy or thermal energy. So the way we would find the kinetic energies at the outlet is using the first law. Just like what we did, for the compressor and the nozzle. The only difference in the analysis here is we should keep the kinetic energy terms in our total enthalpy flux terms. So recall when we write out the first law, there's that summation of m dot times h plus kinetic energy plus potential energy. What you want to do is you want to keep the kinetic energies in that. What I'm specifically referring to here is this term. We want to keep that kinetic energy in because that's the whole purpose of a nozzle is to change the kinetic energy, and so we want to see how that changes. So here's our first law. First term is 0 because it's steady state operation that we care about. Here we neglect only the potential energy. Generally, these nozzles are not big devices, so you're not changing elevation by very much, so we can neglect those kinetic energies typically, especially if you're dealing with a gas. If you're dealing with a gas, then you'd have to have huge elevation changes to have any appreciable potential energy change. The heat transfer term is 0 because it's adiabatic. And here there's no work because it's a passive device. There are no moving parts, no electricity, no springs, no rotating shafts. So then what you're left with when all is said and done is h plus 1/2 v squared 1 is h plus 1/2 v squared 2. When you write it out, so we could then solve for v2 squared. That'll be v1 squared plus 2 times, should be h1 minus h2. Right? So we can do that for the actual case, and we can do it for the isentropic case. So when we do that and substitute it back into our definition for the nozzle isentropic efficiency, You have the actual case in the numerator. Divided by the isentropic case in the denominator. It's the same inlet velocity, so it's still V1 squared. Still the same inlet temperature and pressure, so it's still H1. The only thing that's different is the downstream specific enthalpy, H2S. Actually, we're trying to do kinetic energy, so we'd really take the whole thing, divide by 2. So that gets rid of the 2 there. That makes it consistent with our definition. So there's how we calculate the nozzle isentropic efficiency. And just like with the compressor and turbine, we generally know the inlet conditions, so we would know the inlet velocity, you'd know the inlet temperature and pressure, so you could find the inlet specific enthalpy. In the actual case, you would measure the outlet temperature and pressure, so you could find the specific enthalpy at the outlet. And then for the isentropic case, you would know that the specific entropy remains the same between state 1 and state 2, so you could find the specific enthalpy for the isentropic case, just like what we did with the compressor and turbine. So let me sketch this out on a TS diagram. So when you go through a nozzle, the pressure decreases typically. Well, I shouldn't say typically, it just does. So we're going from a higher pressure to a lower pressure in the nozzle. So here's our state 1, temperature T1, specific entropy S1. And then in the actual case, the entropy increases. So there's our state 2. That's what our path looks like. So here's our T2 and our S2. And then our isentropic case, we go to the same isobar. Here's point 2s. The specific entropy at 2s is the same as the specific entropy at state 1 because it's isentropic. And then there's our T2s. And the T2s is smaller than T2 because for the isentropic case, we're getting more energy into the kinetic energy rather than into the thermal energy. So the thermal energy is a little bit smaller than the actual case. These TS diagrams are just kind of handy to just visualize what these processes look like and kind of give you a quick qualitative feel for how properties may change. Okay, we'll go ahead and end the lecture here, and then I'll go through a couple of examples in separate videos.